any second now. There we go.
So from what I know about glue, it's not really about identity as much as it's about single sign-on. So it's not, I don't think it's directly correlating with what we are supposed to be working on. So it's just an implementation of, once you decide, who your identities are, it provides central database and central authentication for your distributed applications everywhere. So yes, OpenID, but plus also like two-factor authentication, FIDO2, and all the other things.
Makes sense. So it's like an authentication server.
Right.
Yeah.
Yeah, single sign-on specifically.
Yeah.
Cool. All right, anything else, or should we let Mike get started? Go for it, Mike. And
cool. Let me present again. So thanks for having me.
Thanks for agreeing to present on a moment's notice.
Not a problem. If it's a little rough, though, that's the explanation. That's my excuse. Can everyone see? Yeah?
Yeah.
All right, cool. So I'm Mike Malone. I've been hanging out in these working groups since, I think, the first one, if not the first one, pretty early. Been super interesting so far. I have some background in open source and open standards. I've worked with Django and Cassandra when they were pretty young projects. I hung around and helped out a little bit on the OAuth and OpenID spec processes, the early on, like pre-IETF days of OAuth, like OAuth 1.0. And these days, I run a company called Small Step. And like broadly, for the purposes of this group, probably the best way to explain it is like we do certificate-based public key infrastructure stuff. So like internal CA and certificate lifecycle management stuff. We have this we're an open core company. So we have an open source tool chain, like our core technology is all open source. It's two pieces, Step CA and Step, which are an online certificate authority and a command line tool for primarily for managing certificates, but it does a bunch of other security related stuff too. So I guess I have some background in certificate-based public key infrastructure and identity, which is really what I wanted to talk about today, because sort of as I watched the presentations, we've talked a lot about signing stuff and how that's sort of an important thing to figure out if we're trying to secure the software supply chain, and talked less about how these signing keys are issued and distributed and renewed and revoked and just overall managed. And certificates are a way to do that in the surrounding infrastructure. So I thought it might be interesting to sort of go through the status quo and sort of some of the protocols and standards that exist today in certificate-based public key infrastructure, and I think that might be relevant to the group. So that's the plan. So here's a sort of brief agenda. I'm going to start really almost from nothing. So hopefully this isn't too sort of like rudimentary or too like boring, but hopefully we'll get through that pretty quickly. I like to sort of like start from the beginning, especially with the security stuff, because it's hard to sort of assume what people already know. So I'm gonna go through like what a certificate is and everything. And then I wanted to demo a few little bits that I think are cool in our tool chain that I thought might be sort of relevant to the group, specifically like some workflow stuff around connecting. We were talking a minute ago about OpenID Connect and single sign-on, connecting single sign-on to certificate issuance, which perhaps could be relevant here. And then I have a few slides on some standards and technology that are like maybe a little bit less familiar, but I think are interesting and solve problems in the certificate-based PKI space that, again, are relevant to the working group. And then I'm going to end up with, I think, like one slide on why I think the existing ecosystem isn't going to work for our purposes, but I'll save that for the end. You guys might get to it before I get there, though. So starting at the very, very beginning, I like to sort of start to explain sort of justification for what a certificate is. I like to start like with HMAC, right? So if you know what a hash function is, right, it's a one-way function. Stuff goes in, you get some random stuff out, you can't reverse the process, right? If you take a hash function and you take a shared secret, like I know this shared secret and Kim knows the shared secret, for example, I could take the shared secret in a message, run it through the hash function, and then shoot the message and the result of that hash over to Kim. And then Kim also knows the shared secret, so she can run the message I just sent through and the secret through the hash function again, compare the hashes, and if they compare, if they match, then she knows I sent it, because the only way to produce that hash output, right, it's a big random number, is to have known that shared secret and the message. So she knows there's some integrity there, right? Like nobody's changed the message in transit or anything. So that sort of makes sense, except there's a problem, because she sort of knows that I sent it, that I produced that hash, but she also could have produced that hash, right? If there's only two people, that's not a problem because she knows she didn't produce it. But if we all knew the shared secret, then she can't really tell who sent it, right? So enter signatures. There's like, for people who are experts, which I'm sure there are experts here, this is probably annoyingly incorrect, but it's, I think, good enough for our purposes. So signatures are a lot like message authentication codes, except they're using asymmetric cryptography. And I think of like asymmetric cryptography as like a magical gift from mathematics to computer science, because it lets you do this thing that like really can't do any other way. So you have, instead of having one shared key, you have two keys. You have a public key and a private key. And you can sign something, which is sort of like producing an HMAC with the private key, but you can verify that signature with the public key, right? So signatures let you prove someone has possession of a private key without knowing the private key yourself. So Kim can verify my signature without having the private key, which means she can't generate a signature. So everybody in the room could have the public key, and I can sign something, and you can all know for sure it's coming from me and not somebody else in the room, right? So that's a pretty powerful primitive. And in authentication, you know, the way this typically works, and again, this is a huge oversimplification, but in a protocol like TLS, if I wanted to know I was talking to Kim, say, I could produce a big random number myself and send it over to Kim, and just be like, hey, Kim, sign this big random number and send it back to me, right? And if she's able to do that, then I verify it with her public key. I know that I'm talking to Kim, because that signature wouldn't exist in the world unless Kim had signed the big random number that I just produced, right? So again, gross oversimplification, but like roughly that's how authentication, which is, I work generally more in the authentication world than the code signing world, but there's a lot of overlap. Anyways, back to the sort of story arc here. Asymmetric crypto is great, but you need to know the public key of everybody that you're talking to, right? And the way that you learn public keys has to be secure. Like, we can trust the crypto, right? But if I'm able to lie and tell Kim that my public key or like Dan's public key is my public key, right? Then I could pretend to be Dan, right? So the key distribution, it's really important that the key distribution is also secure. And that can be really hard. It's hard to scale and keep secure, right? So enter certificates. I feel like this is the reason I sort of go through the story arc, is I feel like the complexity of certificates is somewhat overblown. There's a lot more to it than what's on this slide when you get into practice, but really all a certificate is a data structure that binds a name to a public key, right? So You think of it as like it's not a JSON object, but like a JSON object with two properties, a name and a public key. And then the certificate itself, that data, is signed by a certificate authority. So you can think of it as a statement, like some issuer, some authority says that Mike's public key is X, signed authority, right? And that means instead of having this like N-to-M problem where everybody has to know everybody else's public key, it's sufficient for everybody to just know the certificate authority's public key, right? And you can learn other people's public keys using certificates. And it doesn't matter how you get the certificate because the certificate is signed. So you have this thing called data origin authenticity. Like, you know that it came from the certificate authority somehow because it's signed by the certificate authority. So you can receive the certificate through an insecure channel and still trust it. And how the certificate is usually received is directly from the person signing something. So like in a TLS handshake, when I send Kim a big random number, she sends back a signature over that number and her certificate. So I didn't know Kim's public key before the handshake, but I'm learning it in the handshake. And then I verify the signature on the certificate, and now I know her public key, and now I can verify her signature over the big random number, and now I know I'm talking to Kim, right? So this is a big thing that certificates do, is they help solve this key distribution problem. You don't need things like key servers to tell you who owns which public key. So I like to throw this in here too. This is a real X509 certificate, and as you can see, it has a lot of stuff in addition to just a name and a public key. A lot of it's sort of scaffolding stuff and obscure stuff that you don't necessarily need to know about. Certificates also tend to include stuff like what the key is supposed to be used for, right? So like key uses, some keys are meant for signing, some keys are meant for encryption. So you can throw that in a certificate. That way, things that are using the certificate know not to misuse it. An important thing here is a lifetime, right? Once a certificate is signed, unless you have some additional infrastructure mechanisms in place, it's going to be trusted forever, right? So lifetimes are usually thrown in there, right? So begin date and an end date. So only trust the certificate between these two dates. There's a bunch of policy stuff and extensions and metadata, but at its core, it's binding a name to a public key. So that's what a certificate does. So a few more definitions real quick. I just want to run through these because sometimes I just like use some of these terms in passing, and I want to make sure everyone, I don't even know if these are like my definitions anyways. People may disagree, but so public key infrastructure is just code processes, all this stuff that distributes, verifies, renews, and or revokes certificates and keys. So it's like the umbrella term. Certificate authority is a thing that signs or issues certificates. A root certificate is a certificate that contains the CA's public key. So it's used to verify certificate signatures. Again, a certificate is just a data structure that binds a public key and a name, and it's signed by a CA. A subscriber is a named subject of a certificate that's issued by a CA. So it's just a thing that has its own certificate. A relying party is a thing that uses a certificate to authenticate somebody else, right? So like if Kim had a certificate and she was authenticating to me, then Kim's a subscriber and I'm the relying party. TLS, you guys know what that is. X509 is a standard certificate format used by TLS. And then a leaf certificate is just a certificate that belongs to a subscriber as opposed to a CA certificate. So, and then I put this slide in here because I like to differentiate between when people think of certificate-based public key infrastructure, I think the first thing that pops into their head is web PKI, which is not even a term that people hear often because generally we just call it like PKI, like the PKI, because it's what people think of when they think of certificate-based public key infrastructure is the web. So Web PKI is the public key infrastructure that your browser uses to securely connect to websites, right? When you see HTTPS and the URI, these are like the Let's Encrypt certificates. It's mostly standardized. The big standards are RFC 5280. I think there's an update to that one, but that's the one that I know off the top of my head. And CA Browser Forum, which is more of sort of a policy statement and agreement between the browsers and the certificate authorities on like how certificates are issued and some details. So an interesting aspect of Web PKI is we talked about like these root certificates. Everyone has to know the root certificate public keys. These are distributed in a quote trust store with your browser or operating system. So there are root programs. There were 3 root programs: Apple, Microsoft, and Mozilla ran root programs, but I think Google actually just started one. Google was using Mozilla's until I think just a couple of weeks ago. They kicked off, I think announced that they're gonna have their own root program. So these trust stores are shipped. So your computer browser comes with a bunch of certificate authorities that are already trusted, right? There are over 100 of them. There are a bunch. So the Web PKI is really important because Web PKI certificates are trusted by default by browsers and pretty much everything else that uses TLS, right? So there's no configuration, no trust bootstrapping required. That's already done for you. And then what I do most days is talk to people about internal public key infrastructure. So that is PKI that you run yourself for your own stuff, but you can think of this as like any other PKI, right? The advantage of not using Web PKI is you have a lot more control and flexibility. So Web PKI CAs are bound by like the CA browser forum rules. They can only issue certificates under a very narrow set of conditions. They have to prove ownership of the names that they're issuing certificates for in a very particular way. They can only issue certificates for fully qualified domain names that are in public DNS. And so there are a lot of rules and restrictions around lifetime of certificates and stuff like that. Whereas, you know, if you design your own public key infrastructure, you control all of that. You control enrollment, renewal, certificate lifetimes, authorizations, identity proofing, all your policy and everything. You also control your system security. So instead of relying on the security of 100 plus Web PKI certificate authorities, you know exactly who can issue, right? The downside is you have to do it yourself, right? Okay, so that's my background on public certificate-based public key infrastructure. I have this blog post, if anyone's interested, where it's a long read. It's like 45 minutes, but it goes in like depth on everything I know, which I'm sure isn't everything, but everything I know or knew at the time when I wrote this about public key infrastructure. It goes a lot more into like formatting and stuff like that. So just thought I'd throw that up here. Okay, so that's that. So now we know what certificates are. We have sort of a grounding in like, you know, the terminology and whatnot. So I wanted to talk real quick about certificate lifecycle. So these are like key moments in certificate management. So there's bootstrapping, right? If you don't already trust a root certificate authority, you need to bootstrap and figure out how to sort of establish trust in a root certificate authority. Then there's getting a certificate, which is I'm calling provisioning here, renewing a certificate before it expires, and revoking a certificate. So these are all very important aspects. And I'm going to jump into a demo here in a second. And the thing I want to demo is connecting OAuth OIDC single sign-on to certificate issuance, which I think is a really neat workflow and something that could be useful or interesting to the working group here. So if you're not familiar with OAuth OIDC, OAuth OpenID Connect, it's sort of the merger between the OAuth authorization framework and the OpenID authentication framework. It's a single sign-on protocol. Like people jokingly call it SAML with curly braces. So if you're familiar with SAML, you're pretty much familiar with OAuth OIDC. It's supported by pretty much every major identity provider. And if you haven't heard of it, you've definitely used it because it's used for like social sign-in and you know, Google uses it. So let me show you a quick demo of some stuff over here. So I'm running our open source certificate authority in this tab. And here's the flow I wanted to demonstrate. So getting a certificate, the point of this, I guess, is that getting a certificate doesn't have to be hard. So I'm going to run step CA certificate mike@smallstep.com. So mike@smallstep.com is the name that I want in my certificate. So it's the subject name. And then actually, before I do this, pretty sure I already have these. Yep. So then I'm going to say I want to write my cert out to mike.cert and my key out to mike.key. And when I hit enter here, the step command line tool is going to say like, okay, cool. How do you want to prove that you're mike@smallstep.com? How do you want to do enrollment? And I have a few different provisioners configured here for enrollment. And I'm going to choose this Google OpenID Connect provisioner. And when I do that, it's going to launch the single sign-on flow in my browser. And I'm going to log in as mike@smallstep.com. And it's going to get redirected back. And what happened here is on the redirect back, my client here got an OIDC identity token, which is a signed assertion issued by Google saying, hey, this is mike@smallstep.com. Generated a new key pair, generated a certificate signing request, submitted this certificate signing request along with the OIDC identity token to my certificate authority over here, which verified that token, which proved that I'm mike@smallstep.com and authorized me to get a certificate from mike@smallstep.com. So if I run set certificate inspect -- short mike.cert, you can see I got a certificate here with mike@smallstep.com as a subject. We also put in like your user ID. That's just how our OIDC provisioner works by default. So yeah, this allows you to sort of connect your existing identity infrastructure to a certificate-based public key infrastructure. So you can imagine like, a certificate authority running and using social sign-in to issue certificates in this way. Once you have a certificate, you can do cool stuff with those certificates. So we've been talking a lot about like TLS. I wanted to show another standard real quick. So I'm going to use JWS, JSON Web Signing, to sign something. So JWS, if I think I have a slide on it in a second, but if you've heard of JOTs, JSON Web Tokens, or JWTs, it's part of this Jose group of standards that's all like JSON encryption stuff and signing stuff. So JWS is JSON Web Signing, and it's just a signing standard. So we happen to have JWS support built into the step command line tool. So I can do step crypto JWS sign some file.txt. And then the JWS standard has this cool sort of integration with X509 certs. So I can pass in --X5C cert and --X5C key and pass in my X509 certificate and key. And I'm going to get this big base64 encoded thing back. But the format of a JWS, you can see, they're probably hard to see, but I'm going to highlight to the first dot here. The format of a JSON web signature is base64 encoded JSON header dot base64 encoded payload dot base64 encoded signature. So the header is the interesting bit in this case. So I'm going to base64 decode it for us real quick. -d hype to JQ. They did something wrong. This worked when I did it by myself. Try again.
That looks like JSON.
Yeah, it does. I was trying to pipe it through JQ. It looks like it's not terminated. Anyways, you can see there's an algorithm here, a key ID. I was hoping to format it nicely for you guys, but this is the interesting bit. So you can see in here is this X5C property, and then there's a list. And if you're a like X509 nerd, you'll probably recognize this MII beginning. These are X509 certs, base 64 encoded X509 certs in the header of this this data structure. So sort of like TLS, the neat thing about this is if I send this to you and you trust the root certificate, you can verify that it was sent by me without already knowing my public key. Because again, in this structure, my certificate is included, right? That was the point I was trying to make. Unfortunately, I didn't get to make it as eloquently as I'd hoped. Yeah. Anyways, we inspected cert. Oh, I wanted to show a couple quick additional workflow things. So as I mentioned, short cert. Certs expire. We issue short-lived certs by default, which is good practice. You want things to be trusted for a shorter duration. It's good, but you need, if you're going to keep using the cert after expiry, you need to be able to renew it. So again, renewal doesn't have to be hard. We can renew like that, and now I have an extended lifetime, and that is literally just using a mutual TLS request as a certificate authority, and you can renew that way. We also have a revocation, so I can revoke. So I just revoked that cert, and now if I try to renew it again, I'm going to get an error because it's been revoked, right? So the last thing I wanted to show is sort of like a live demo is just what this might look like in a workflow. And I'm going to demonstrate how we've integrated this certificate lifecycle management stuff into SSH. So OpenSSH, again, I have a slide on this in a second with more details on it. OpenSSH actually supports certificate authentication, and it has a bunch of neat benefits. Let me show it to you first, and then I can talk a little bit more about it. If I SSH to this EC2 instance, we've hooked this in, hooked into, this is all standard OpenSSH. So this is like the normal OpenSSH client. We've configured it to use certificate authentication. And if I don't already have a certificate, use the single sign-on flow that I just demonstrated automatically to obtain a certificate in band in the connection. So if I SSH to this server, you're going to see that same flow that we just looked at before. It's going to be like, oh, you're not logged in. You're not going to be able to connect to the server. So go and get a certificate first using this OIDC flow. So I'm going to sign in my browser. In this case, I'm using Okta, not G Suite. I get redirected back. And in band with this request, that same flow that we were just talking about happened. So I got an OAuth OIDC identity token. I generated a new key pair. I exchanged it with the CA and got an SSH certificate. The key material in this case, we just jam into SSH agent, which is like an in-memory. It's a little process that runs that on a Unix domain socket that the SSH client can talk to. So all the key material is held in memory. So it's ephemeral, short-lived keys held in memory, never touching disk. Better security and improves operations because you don't have to do the key distribution stuff, and pretty good user experience too. Because this works on SSH, by the way, works with SSH, I should say, and Git can use SSH as a transport. This works with Git as well, and like GitHub can use SSH certificates. And okay, let me get back to the deck. All right. So relevant standards. So the first one, again, OpenSSH certificates. They've been in OpenSSH for 10 years. It's not, OpenSSH uses its own certificate format, so it's not X509, whatever. It's still got a lot of benefits. And the interesting thing for our purposes is, I noticed when Damien was talking about OpenSSH signing that he mentioned it works with SSH certificates. So if that stuff gets integrated into Git, you're going to be able to use certificate-based PKI with OpenSSH signing in Git. So there's sort of a path forward for certificate-based PKI in our world. The other standard I thought was sort of just worth discussing real quick is the Jose suite of standards. I talked a bit about them already. Everybody hates them, but everybody also uses them. They're used by OAuth OIDC. The identity tokens that I keep talking about are JOTs. In fact, the Jose suite was largely developed to support OIDC. The probably most relevant two standards for our purposes are the one I was just demoing, the JSON Web Signing standard, which can sign arbitrary stuff. And there's also JSON Web Key, which out of the suite of standards, I think is my favorite. It is a standard way to represent a cryptographic key in JSON. And out of all of the ways I've seen to represent a key, I think it's the best. So if we needed a way to represent a key at some point, I'd say JSON Web Key is the way to go, just my opinion. Okay, so now some stuff that's a little bit more obscure that I thought was relevant. And I'm trying to get through this quickly, by the way, because I want to leave time at the end. The first thing is certificate transparency. So I'm going to sort of set this up as a problem solution to sort of help grok it. So we talked earlier about Web PKI and how there are 100+ certificate authorities that every browser and operating system trusts by default. So any one of those certificate authorities can issue a certificate for google.com, right? And everybody will trust it. And Google didn't like that. Some of these certificate authorities are in China, for example. So certificate transparency is a solution to that problem. So the way certificate transparency works is when a cert is issued, the certificate authority submits it to a certificate transparency log, which returns this sort of receipt that it's been submitted. I think it's called a signed certificate timestamp. It doesn't matter, SCT. It's a proof that you submitted it to the log. And anyone can monitor these CT logs, so they're public. So anything that's been submitted it gets in this append-only log structure, and anyone can see what's been submitted to it. And relying parties like browsers only trust certificates if they have one of these SCTs. So basically, if a certificate hasn't been submitted to public certificate transparency lists, browsers won't trust them. So Web PKI CAs can still issue a certificate for google.com at any time, but browsers won't trust a certificate unless they've been submitted to a CT log, and Google monitors the CT logs, so they'll notice if a CA issues a cert that they didn't ask for, and malicious certificate authorities are removed from root programs and won't be trusted anymore. So there's sort of this detection mechanism now built into the Web PKI that allows people to detect this malicious behavior if it occurs. So that's certificate transparency, and certainly if some sort of certificate-based PKI were used for us, I think you'd want some sort of similar mechanism. Beyond just certificates, though, there's a lot of work going on generalizing this notion of transparency over arbitrary stuff, right? So there's key transparency. You can imagine sort of like a commit log transparency or a release transparency list. The concept of a sort of immutable append-only map of stuff or log of stuff that happens with inclusion proofs is useful. It's a useful security primitive. Google has a project called Trillion, if you haven't checked it out, that does this. That's sort of, I think, the best solution. I don't even know if there are other ones, but Trillion is, I think, the way to go. Blockchain. I'm not a blockchain expert by any means, but I think at a high level, blockchain can probably be made to do a lot of the same stuff as certificate transparency. It's probably overkill. It's probably more decentralized. If you'll notice, CT is still somewhat centralized, right? You have these CT lists. It's a server running somewhere that's issuing these signed statements and the log, right? So it's not fully decentralized the way blockchain is. Blockchain would probably be less efficient more complicated than CT. There's another idea around blockchain though that I think is relevant, which is so there's this conjecture called Zuko's triangle. So this is an identity concept, right? So there's this conjecture called Zuko's triangle that says names in a namespace and like an identity system. There are 3 desirable properties. They should be human readable. In other words, they should be like meaningful and memorable to people. They should be secure. So you shouldn't be able to sort of steal somebody's name. And the naming system should be decentralized. So resolutions and bindings shouldn't require a central authority. And Zuko's conjecture was that you have to choose 2. You can't have all 3. So DNS, for example, is human readable and it's decentralized, but it's insecure. DNSSEC is human readable and secure, but it's centralized. You could use raw public keys to identify people, right? Instead of their like human names, in which case it would be secure and decentralized. Anybody can generate a key pair, but those public keys are big random numbers, so they're not meaningful to humans. So this was a thought that was sort of out there in the world for a while, and then blockchain came along, and Aaron Schwartz wrote this blog post and was like, yeah, no, Zuko's wrong. Blockchain, you can do all 3. And the sort of quick summary, he's this great blog post. It's pretty accessible called Squaring the Triangle. I have the link up here. But I think that the main sort of idea, the way I understand it, is that like if you understand the double spending problem in the blockchain space, where like you only want to be able to spend a piece of currency once, and that's like one of the reasons for the immutable log of like transactions. It's pretty similar to double name assignment, which I think is the big problem that's the conflict between human readable and decentralized. Is if it's human readable, if you have a low entropy name, then you need some authority that says, yeah, you can have that name because nobody else is using it. So it's hard to decentralize the naming and maintain security. Blockchain does that, right? So you can have a blockchain system like a scroll that says like, the first person to add a hash chain to the scroll that says I'm Mike and my public key is X is the person who gets to be Mike forever, right? And that can be decentralized. And then the last thing, interesting bit of tech that I wanted to mention real quick, and this is probably the thing I know least about, but I think it's relevant to the signing space, is this this notion of time. And the reason I wanted to include this is because I don't think it's solved by many systems, including PGP. PGP seems to just assume that keys are never compromised and never rotated or changed, which is an interesting thing to assume. So here's the scenario. I steal your key today. You notice and revoke it. Then I go and I use your key that I stole to sign a commit with yesterday's date in it, right? So there's sort of 2 options here, right? When you revoke the key, like, are you revoking going forward or are you revoking forever? If you revoke forever, now you have all of these old signatures using your key that are no longer trusted. So that's not going to work. But if you revoke only going forward, and if the person making the commit gets to pick the date of the commit, then they can lie and just say it was signed before the key was revoked. So broadly, the solution here is to include a third-party source of authoritative time that's like bound in with the commit. And there's this protocol called rough time that I think would probably be a good solution for this in our world. I think there's some other, there's a thread on my Twitter because I was asking the internet about this yesterday, but like basically the way rough time works is there are these public rough time servers. I think like Cloudflare runs one, and you can shoot a nonce over to them and they'll return with like a tuple of the time and like I think your nonce and like their signature over the time in the nonce. So basically it proves that this nonce existed at this time according to Cloudflare. So if I sent over my signature over my commit to a rough time server and got a signed proof back from Roughtime that said like, hey, this signature existed as of this date, then you guys could all be pretty confident that I signed it before that date, right? Because Cloudflare is saying that the signature existed in the world before that date, right? It's not just me. And then you could include that in the signature package in a header or something like that. I don't know of any. I know this is used in document signing, but I don't know of anything in sort of like release management or code signing that uses this. I could be wrong.
Well, unless of course Cloudflare steals your key and
right. Yeah. So interestingly, Roughtime has sort of. I think you'd have to. Roughtime is a very low level primitive. I think so you can build on it. Roughtime has an answer to that too, which is that you can chain Roughttimes. So what you would do is you get Cloudflare's answer, right? And then you take their signature over like their payload and you submit it to another Roughtime server. And then they return and like now you've sort of chained it, right? And that also lets you detect malice too, because if the other Roughtime server says it's a different time than Cloudflare said, right? Because these are supposed to be like monotonically increasing clocks, then you could sort of demonstrate that like, hey, Cloudflare is lying about what time it is. And if you submit to enough of these Roughtime servers, in theory, you could get pretty good confidence that no one's lying, right?
Yeah, I like I certainly agree with the problem. I do worry that if it's optional, you just don't include it.
Yep.
So.
Yeah. Well, you can make it not optional, right? I guess like I don't know the right answer here. This is I think the problem and a tool that may help solve it, but I actually don't know the landscape here very well. I do know about Roughtime, and I think RFC 3161, a bunch of people were pointing me to, which I think is a time authority. It seems pretty similar in concept, though. Broadly, though, I think you have to appeal to some third-party time authority. I can't think of another way. Actually, I take that back. There is another way, which is I think you can use some form of transparency as well. So if something was submitted to this log structure, data structure, right, append-only log, and it was in the log from yesterday, then you know it was signed yesterday, right? So you could reuse that piece, that bit of architecture, that bit of infrastructure for this purpose.
Assuming again that the signature is included, because if it's only just the message, I'll make the fraudulent message a couple of years ago, and I'll just wait till I get your key.
Yeah, there's a couple of problems here too. That people usually don't know a key is stolen unless because nobody actually advertises. Hey, I got your key. Right? So unless somebody actually leaves their laptop and the laptop is physically stolen, then they start to worry about like, hey, I think my key is stolen. I'm going to go ahead and revoke it. But that's a very unlikely scenario. More likely scenario is going to be that somebody stole it from the disk, and the developer does not know it. So even if you include Roughtime or any scenarios like this, you don't actually get anything out of this because anybody can use Roughtime. Anybody who has the key, but the owner of the key doesn't know the key stolen. There you can't go back and say actually didn't sign it. We at Kernel, we recently released the transparency log specifically for this purpose, saying these commits were pushed at this time, and this is appended to our append-only Git log. Well, Git's not append-only, right? But we replicated fast-forward only to a bunch of places, including infra we don't own. So if that's modified or somebody tries to rewrite history, it will be extremely obvious to everybody that it's been done. So it's tamper evident, it's not tamper proof.
Yeah.
That's
probably a good argument for using transparency over just simple time authority for something like this, I think. And this is just me off the cuff, so I could be totally wrong. But like, yes, a transparency list would also let you detect, possibly, at least give you the tool set. You still have to do some work to detect that somebody is using your key that is not you.
So we've been working on a project that does just this. It's a personality on top of Trillion. And the requirement for a log entry is that there's a signature, a public key, and some sort of artifact that's signed. Okay. And this is then entered into the transparency log, and then you can pop entries off and look for things such as your public key being used as an example. So it's something that's it's a fairly early piece of work, but we're getting towards a usable state now. So yeah,
that's cool. Yeah. And it's taken years for this ecosystem to develop around web PKI. I mean, certificate transparency has existed for a while now. And what's now starting to happen is like vendors, like I think Cloudflare has a free service now where you can enter your domain name and they'll send you an email whenever a certificate is issued for your domain. So you can like imagine layers being developed on top of stuff like that.
Yeah. So the idea of what we're doing is we're not really driving a specific use case with the transparency log. It's more that we're making it easy for people to implement those use cases. So they can work with a simple set of APIs and not have to worry about, you know, how they code an inclusion proof and get a signed tree head and all those sorts of complexities. So this way, somebody can come up with their own manifest. Okay. And as long as there is some sort of signing in there so that we have non-repudiation, so people can't just throw anything in there, then, you know, we can then have a use case where one example that we use is, have I been pwned? You know, the old website where you put your email in and they trawl through all the paste bins to look if your account's been compromised when a website has been hacked. You familiar with the...
Yeah. Mm-hmm.
Yeah. Okay. So a good example there is somebody could build a website on top that monitors the log. Okay. And then you then submit your public key and an email address to this site. Okay. Which runs independent of the transparency log. And then they monitor entries coming into the log. And if they see your public key being used, they could send you an email. Now, most of the time you might think, well, meh, you know, yeah, of course, I just signed ACME project's release. So you just delete the email. But another time it could occur where you are kind of like, well, hold on, I've not been, you know, I've not signed anything. What is this? Do you see what I mean? And then immediately there is obviously some investigation that needs to happen as to, you know, what artifact was signed, you know, what other sort of data sets were associated with that was in the manifest that was used. Now, of course, somebody could sign something and not put it in the transparency log. Okay. But then the question that's begged then is, should you trust something that's not in the transparency log because it's not what everybody else is seeing then? So it's the same as certificate transparency, essentially. Yeah.
The fact
that it's not
trust.
in is a signal in its own right. Yeah.
Do you have is there a link with more information about that, Luke?
Yeah, sure. Yeah, if I'll get it for you.
Cool.
So our README needs a bit of attention. We're kind of we're iterating over the design and coding at the same time. But yeah, there's a website going up shortly as well. So we've done a few things, like we've pulled in Node.js releases and all their signing stuff and entered that in, and just looking for other projects as well to include. But it's relatively easy for somebody to stand up their own instance as well. And we've got some code that's just in review at the moment to add what we're calling pluggable types. So somebody can sort of delegate their own key values within a manifest of what they want to capture. So it could be, for example, compiler version or build system version or developers email, or, you know, whatever sort of specific data sets you wanted to get in.
Cool. You know, the W3C DID working group seems to be active in this kind of topic as well. And that's the decentralized identity working group.
So decentralized identity is hard, which is actually a nice segue into this last slide that I just wanted to throw up, and then we can go back to just sort of discussion. I guess, like, summarizing everything I went through, like, a lot of problems are solved with the tooling and infrastructure that we just went over, right? And transparency is probably one of the most interesting things. So I'm it's interesting that the conversation is going in that direction. But I think existing certificate-based PKI, the way it works sort of with web PKI, is probably too centralized, still too centralized for this working group's purposes. And using, like, maybe you can depend on email addresses as a name, maybe you can depend on OIDC, but I don't know that you could really ask every open source developer to have an email address with an OIDC identity provider, and have a small number of trusted certificate authorities the way that web PKI works. So I think there's a lot that is solved here, but I don't know that it's exactly what this working group is looking for. However, the remaining problems may be easier to solve than fixing PGP style key distribution. So that's sort of where I wanted to leave it. And now I guess we can just go back to discussions. I just wanted to get that out before.
Well, this kind of requires that the certification authority that you use to issue the certificates remains up and available for querying the OCI records and stuff, right? So this ties you in with always on, must be able to access it, utility for verifying signatures.
Not necessarily. You know, I can verify a certificate and a CT log inclusion signature without any online request.
Well, you have to query OCI, right? So you have to query that it's not revoked. If you require a revocation check, yeah, revocation in the web PKI I didn't get into, but it's kind of a tire fire. If you're using super short-lived certs, then revocation is less important. There's also stuff like OCSP stapling, which is like you can have a longer lived certificate and then you get sort of a shorter duration statement from a CA that says, like, for the next 5 minutes, trust me, this certificate hasn't been revoked. Which requires less availability, but yes, for revocation, you generally need some sort of online service.
There's no silver bullet here. You're right.
Right. Yeah.
If you have revocation checks that happens every 5 minutes, and you say, well, let's go to short-term lifetimes of your certificate of, let's say, every 5 minutes, then that means either way, I need to be able to connect every 5 minutes.
Every 5 minutes, right? Yep. Correct. Now, again, perhaps less of a problem than, like, you know, you'd still have the same issue with a key server, for example.
Right, but that's exactly what I'm highlighting, is that this is basically another way of doing a key server.
Yeah, well, I mean, again, fundamentally, I'd say certificates are a way to distribute keys. And arguably, right? Like I suppose I am presenting the case that they're perhaps a better way, but that's certainly arguable, debatable.
If the trade-off is connectivity, then I think that they're equivalent. The reason why you would go with public key approach over symmetric key servers is that the symmetric key case is that anyone who knows the symmetric key can masquerade as the other entity.
No, I'm not arguing for symmetric keys. I'm just saying the key server is in PGP key server. So there's still asymmetric. So and the certification is done by some other means. For example, when you're retrieving a certificate, you could use a HTTPS connection. So you're kind of delegating your trust over to SSL certificate or to the certification authority that way. Or you can trust that all of the keys that this key server presents are trusted because they are signed by the key server itself, for example. Yeah. That's also trusted on certification.
Yeah. So that in that case, in the PGP key server case, the role of revocation and certification are combined into a database, and you're just relying on your ability to access the database that's in the key server.
Yes. Yeah. This is the two different ways of doing the same thing, basically.
Yeah. So part of the argument, Constantine, I think, is that there's also a lot of infrastructure around certificate-based PKI that could be reused possibly, and maybe I know the sort of PGP style case less well. So perhaps the same infrastructure exists there, but I'd say that's part of the argument for certificate-based PKI as well. You know, the fact that there are standards and protocols around a lot of this stuff that already exist.
Awesome. Well, we're a couple minutes over. Thanks a lot, Mike. I think we had
Sure.
some conversation there. David just asked for the slides link. I think you have that. You can drop that into the agenda in chat. Otherwise, awesome. Yeah, thanks. I thought this was really useful. We'll get it up on YouTube ASAP.
Thanks, guys. Have a good day.
Yes, and thank you so much.
Thanks.